Hello and welcome. Today we're going to be doing some examples of matrix multiplication. And I think it's just good, it's probably best to learn how to do matrix multiplication by just doing lots of examples until it becomes really fluent. There's no better way to do it. So let's talk again about matrix multiplication. In the abstract then, of course, we have a matrix that's n by m, and we want to multiply it by a matrix that's m by p. And where we require, these must be the same for AB to exist. Okay, so we need those to be the same, and the output, C, is going to be n by p. It'll be a different dimension, n by p. And you see that so it's going to have the same number of rows as A and the same number of columns as B. Okay, so that's how it works. All right, so that's in general, and we had written down there, so if A is equal to Aij and B is equal to B Kj, all right. Sorry, I need to restate that here. We want, that has to be equal to jk, right? So here, I is going to run from 1 all the way to n, and j here is going to run all the way from 1 all the way to m, okay? Good. All right, and here, j is going to have to run all the way to m, and k is going to run 1 all the way to p. All right, and it's clear here that these have to be the same. These have to be the same here, okay? And then, of course, C, the matrix C is C I K, where I is going to run from 1 all the way to n, and k is going to run from 1 all the way to p. All right, and so in general, the theory of matrix multiplication says that CIK has to be equal to the sum of, from J is equal to 1 all the way to M of AIJ and then BJK. We see here that we're summing over the number of columns of A right here, and we're multiplying all of these columns for every row. So that's a row. And we get whatever column it is, we simply have to sum over these products of A and B's like so. All right, so this, of course, is, I have to say, hard to visualize. This is a hard to visualize thing. So let's see if we can come up with some shortcuts. A shortcut or some sort of a simplifying principle that can help. It can help understand this better. Okay, so let's get right to that. So what we're really going to talk about now is actually a matrix. A can be thought of as actually A as a set of columns. Okay, so A, of course, we can write as A11, A12, all the way to A1n. All right, sorry, no, M. Right, and all the way down to N1. And it goes all the way down to ANM. Okay, so that's how you'd write the matrix. But I really want to write it as follows. This is actually a set of vectors, of column vectors. Column vectors. Each vector we can write as follows. A1, 1, A21 all the way to AN1, A12 A22 all the way to AN2, and so on as follows, A1M all the way to ANM as follows. All right, so another way to think about it, and I want to define now what we call a weighted sum of column vectors. So a weighted sum of, so this is a weighted sum of column vectors. All right, so here's our column vectors right here. And we have m of them. So we have m vectors in A. Okay, so we have m vectors in A, and what I want to define is this weighted sum, so I'll call it weighted sum, where we're going to say that now, we have this weight with weights. I'll call them, let's say we call them W1, W2, all the way to Wm. Again, because there's m vectors, we need m weights. Sorry, I should say m weights. Okay, like that. So a weighted sum, Ws, is going to be equal to these m vectors in A. I'm going to give these a name. I'm going to call this V1. I'm going to call that V2. And I'll put the little arrow over it all the way to Vm. And that arrow just means it's a column vector. Right? And then, of course, what we're going to say is the weighted sum then is going to be V1 times W1 plus W2 times V2 plus ... all the way WM VM. We call it a weighted sum because we think of these as different weights. Now, so you might be unfamiliar with the idea of a weighted sum. The idea that this is a sum where we're weighting all of these different vectors according to whatever these numbers are. These are just some numbers. Okay, so of course the most classic weighted sum ever is called an average. So you might remember an average, of course, is if you have some data, call them xi, right, from I equals 1 all the way to m, right? All right, and so the average then is going to be equal to the sum of all those numbers divided by m, the number of numbers. Well, I can write that out as a weighted sum. That's 1 over m xi, or x1, sorry, plus 1 over m x2, all the way 1 over m plus xm. In here, all those weights, they're all equal weights. So in the particular case of an average, we're talking about an equal weighting of all of the data. And that's very important if you want to do an average over some data. And each data point you want to contribute equally to the average. But in some other contexts, you might want a different sort of average that's actually weighted, that some observations, some data points are actually weighted more than others. And that's, of course, when you'd want to change the weights. And that's precisely how we're going to think of doing matrix multiplication here. All right, so with this, let's see if we can go to the next page. So how does weighted sums, so weighted sums to do matrix multiplication. Okay, so how do you do this? Well, again, we're gonna, A now is going to be the set of column vectors, and I'll just, like that, there's m of them, and I can call them V1, V2, and V3, or so all the way to Vm, and so on and so forth. And then what I'm going to do is actually multiply it by a vector called W, all right? And that'll be a column vector that also has a length m, right? Well, then A times W, the vector, is going to be the weighted sum. It's going to be the sum of vi times wi, I ranging from 1 all the way to m. Okay. All right, now what if I have B now is my matrix? I'm going to write it here, and it's going to have, of course, m rows. M rows. And I can write this is now filled with, and it's going to have p columns. All right, and that's because it is m by p, right? I'm going to call this is going to be B11 all the way to BM1, and then the last one will be, of course, B1P all the way to BMP, all right, and then everything in between. There's a bunch in the middle as well. All right, well now, A times B then is going to be actually going to be equal to A times, I'm going to call this vector here B1, the vector, and that's going to be B, some in the middle, BK, all the way to BP, right there. And this is going to be B1, the vector. That'll be the first column in my result. Whatever this result here, I'm going to call this thing C. And then the second column will be A times B2, the vector, all the way A times BP, the vector. So that's a little bit better way to organize the multiplications that have to go on. So we really think of A as the columns, and then we think of B as weights. Okay, and then each column of the result, A times B, is a different weighted sum. Okay, so let's do some examples now to help clarify this. And we're going to start with a really simple one. We're going to start with 1, 2, 3, 4. That's my matrix. I'm going to call that A. Okay, and then of course I'm going to have a matrix B, and I'm going to make it a big matrix. I'm going to actually make it equal to 1, 2, 1, negative 1, 3, negative 2. Okay, all right, so the question then is, so this is B, and let's look at their dimensions first. This is going to be 2 by 2. We see this is 2 by 3. All right, so the question then is, what is C? Well, C is clearly, remember, these two dimensions have to be the same. And the result will always be the outside edge dimension, so it's going to be 2 by 3. All right, again, these are the weights. These column vectors are weights. We think of them as weights, and we think, and these right here are the column vectors that are going to be weighted. Okay, so what we do now is write this as follows. I'm going to make this really big. You'll get really quick at doing this later on. You won't have to write all this out, but this is just a way to help you understand what to do. So the first column in my result, and we're going to have 3 of them. Actually, I think I might need to give myself even more space just to help clarify and to make this really clear what's happening. Okay, so here we go. I have 1, 3. That's my first column. I'm going to weight it by 1. And then I'm going to go plus, there'll be a negative 1. That's my next weight here. I'm going to add that to the other column vector, 2, 4. I'm going to just crop that down a bit so I can, later on, I want to write a little bit below it. Okay, that's better. All right, and that whole thing is going to be column 1 of my matrix C. So again, this right here, this entry here and this entry here, those are the two weights that I'm multiplying by the two column vectors. I'm going to add that whole thing up, and that's going to give me column number 1. I even put a little comma in there to help me kind of organize my work. Right, and then again, 1, 3. Oops, I'm going to back that up. 1, 3. And now I'm going to use the weights from the second column of B here. That's going to be 2 plus 3. Now the other weight will be 2 and 4. The other vector will be 2, 4. And that'll be my result for the second column of my result. Comma again. I'm putting lots of brackets and parentheses here just to help organize our work. Again, the column vectors are always the same. It's how we're weighting them which is changing. So again, now the weights are 1, -2, so I'm going to put a 1 there, and then I'm going to put a -2 there. Right, we can do this and put this all together then. We see that we have 1, 1, and -1 times 2. That's going to give me a -1 right there. Now when I add these two together, I do a weighted sum. I see a 3, and then it's going to be a -4, so again it's going to be -1. All right, now we go to the next column. We're going to add this up. We see we have 2, and then we have so that 3 is going to multiply by that 2, and that's going to be a 6 plus 2, so that's going to be 8. We have a 6 there and a 12 there, so that's going to give us an 18. Okay. Finally here, we go to the last column of our matrix C, our result. This is going to be C down here, and that's going to be 1. We have a -2 times a 2, that's going to be a -4, plus a 1, that's going to be a -3. And then we have a 3 times a -8, so that's going to give us a -5. So that's our result. That's how we get it. So this is one way to help organize our work, to help see how to get our results from matrix multiplication. So there's a good example. Let's do another one. Now I'm going to do my matrix A is going to be a column vector, just a single column vector, 1, 2. And now I'm going to do a matrix B. I'm going to say this matrix is, I'll call it -1 and then 5. Okay, so here this is what we call a column vector. And here, of course, we call this is actually just a single row vector. All right, so let's multiply these together. So let's look at this. So this is, of course, is a 2 by 1 matrix, and this is a 1 by 2 matrix. All right. So in this, now let's ask the question: how do we multiply A? Actually, what I'm going to do is I'm going to multiply B times A first. Okay. So that's 2 by 1. And that's 1 by 2. All right. So the dimensions are shared on the inner dimensions there. So that's good. So the result C is actually going to be 1 by 1. It's just going to be a single number. All right, so let's write this out. This is going to be -1, 5, and that's going to be 1, 2. That's B, and this is A, like that. We see here that the column in this case is just a single -1, and then the column vector here is going to be a 5, and so we have to just do a weighted sum of -1 and 5, and that's clearly going to be, the result is going to be a 1 by 1 matrix, a single number, and it's going to be -1 plus, and then 5 times 2, that's the weight there, and that's going to be 10, so it's going to be -9. Okay, so now let's try doing the matrix multiplication the other way. So now we're going to have 2 by 1, 1 by 2, right, so the inner dimensions are shared, and then we're going to get a result C that's now 2 by 2. Okay, so this is really interesting. So now I write that down, 1, 2, times -1, 5, the row vector. So we see here, now we have just a single column vector in A, and that's B. And so it's actually a really quite simple weight. The weight is going to be -1 times 1, 2. And the next row is going to be weighted by 5 times, again, the only single column vector in A, 1, 2. All right, so we can write that out further. That's going to be -1, -2. Then here it's going to be 5, 10. So that's our result in this case. So clearly, A times B does not equal B times A because they are not the same dimension. So of course here again, this is just another aspect or another example here of that basically matrix multiplication is not commutative. Okay, so hopefully that gives you some good examples of how to do matrix multiplication and a little bit clearer understanding of some of the simplifying methods that can help you get into it. After you do it for a while, you'll probably find your own way, but hopefully this helps see how to do matrix multiplication. All right, thank you very much.